This is section 3.5, Limits at Infinity. So in this topic, we're going to be talking about what happens at the end of the function, called end behavior. That is, when you get really far out to the right as x approaches positive infinity and really far to the left as x approaches negative infinity, what is happening to that function? So from negative infinity to infinity, what's the behavior of the function? So if you look at figure 3.32, that's the graph of f of x equals 3x squared divided by x squared plus 1. And it seems pretty clear from the graph that the function outputs are approaching 3 as x approaches infinity on the right side, and f of x is also approaching 3 as x approaches negative infinity on the left side. So graphically we can see that f of x appears to approach 3 as x increases without bound or decreases without bound. We can come to the same conclusion by making a table of values, and this is a numerical approach as opposed to a graphical approach, where you look at numbers that are getting further and further from 0, 1, 10, 100, 1,000, etc., negative 1, negative 10, negative 100, etc., and looking at the evidence that those values are getting closer and closer to 3 helps you make that determination. So the table and the graph suggest that the function values approach 3 as x increases without bound and decreases without bound. And so the notation for that is very similar to the notation we had as x approached a constant value. This is going to be as x approaches, say, negative infinity. And that limit of the function is 3. And the limit as x approaches infinity for this function is also 3. And what this implies, both of them separately, but they happen to be the same number, is that as x approaches negative infinity, the function is approaching a constant value, which means that we could conclude that the graph of f has a horizontal asymptote and the equation of that asymptote, since it's a horizontal line, is y equals a number, and of course that number is 3. And so the same conclusion is drawn as x approaches positive infinity, that f has a horizontal asymptote at y equals 3. All right, so the definition of limits at infinity, I'm not extremely concerned about your totally understanding what that means. It just means that as x increases without bound or decreases without bound, the function values become arbitrarily close to a constant value, which we'll call L, and that you can make the distance an arbitrary small size, and that the difference between our function and its limit, like between this function and 3, for example, is arbitrarily small. So just take epsilon, which is some small positive number, and when you get past a certain point on the graph, the difference between our graph and the limit, that horizontal line, is smaller than that small number you gave. And you can make that number as small as you want, which means that the graph and the line, horizontal line, only get closer and closer. Well, actually the line isn't moving, so the graph gets closer and closer to that line. So you can see on the picture, figure 3.33, that if you allow yourself a small amount above and below your limit, at some point the graph will not exceed epsilon away from the limit, either above or below. And so if you make epsilon really small, of course that means that you're just getting closer and closer to the function being the same output as L, the horizontal line's y value. Okay. And so that leads us to the statement, the definition of a horizontal asymptote. If you take a limit as x approaches positive or negative infinity and get a constant L as an answer, then you will have an asymptote at y equals L, which is what we concluded earlier. Now, that does imply that we have at most two different horizontal asymptotes. You can have one on the left and one on the right, and that's it. You can't have more than that. And sometimes, like you saw in this one that I've written y equals 3 for on both sides, sometimes it's the same value. So there's just really one asymptote that's used at both ends of the function. Now, as far as properties of limits, there are some limits that are the same. If you have a limit of a sum of functions, then you can take the limit of each one individually. If you have a limit of a product of functions, you can take the limit of the first times the limit of the second. And that would be true if you were saying x approaches negative infinity as well. Now, theorem 3.10 is really helpful. If ever you're taking the limit as x approaches infinity or negative infinity, and typically the rules are written for positive infinity, but it works for negative infinity as well. If you are taking the limit of a constant over any power of x that is positive, so r is positive, and we'll further stipulate that r is rational, and you know what a rational number is. It's any number that can be written as the quotient of two integers, like 2 over 3, negative 12 over 7, 4, which is 4 over 1. As long as you're raising x to a positive rational power, the denominator will only get bigger and bigger as you multiply x, multiply by itself and by itself and by itself. And as x goes to infinity, that denominator becomes infinitely large, and any constant like 3 divided by 1,000,000, and then divided by 1,000,000,000, and then divided by 1,000,000,000, that answer is getting closer and closer to 0. So if you want to test this, just type 3 over 100, 3 over 1,000, 3 over 10,000, 3 over 100,000, 3 over 1,000,000, 3 over 1,000,000,000, and notice how your answers are getting closer and closer to 0. And that works whether it's positive or negative infinity that x is approaching. All right, so, well, the one for negative infinity is actually interesting because if r were, say, a half, you can't take this, the like square root of a negative number. So we would have to say that when x is approaching negative infinity, you have to be careful about what numbers r can be. Basically, if x up to the r is defined when x is negative, if that's the case, when x is negative, then this too will go to 0. Of course, if it's r is 1/2, you won't have a limit as x goes to negative infinity for that one. So it has to be a defined value. X star. Okay, so let's practice this a little bit with an example. Find the limit as x approaches infinity of the difference 5 minus 2 over x squared. And so since that's a difference, we can split that into two limits using one of the properties we just mentioned. So take the limit of 5 minus the limit of that rational expression, 2 over x squared. And of course, the limit of a constant is still that constant minus, and this 2 is a constant over a rational power of x that's positive. Power is positive 2. And so that will, according to the theorem that we just mentioned, that will head towards 0. 5 minus 0, of course, is 5. So we can conclude from that that the function f of x equals 5 minus 2 over x squared has a horizontal asymptote on the right side, on the positive x value side, and it's located at y equals the limit we got, 5. Okay. And if we were to look at a graph of this function, it would look something like this. On the right side, and if we looked at the entire graph, it would look like this. Oops, I drew that a little bit too high, sorry. Try that again. Okay, well, I'll just leave it close enough. And the idea is, if you look at a better graph, perhaps one that's on a calculator, of this function, and also graph y equals 5, you'll see that on both sides, y equals 5 is a horizontal asymptote, not just on the right side as we found, but also on the left side. Okay, so now let's do another example. Find the limit, which is the limit as x approaches infinity of 2x minus 1 over x plus 1. And I'm going to ask that you learn this trick I'm about to tell you about. If x is approaching infinity or negative infinity, the trick I want you to learn is find the highest power of x in the denominator. Since x plus 1 is our denominator, the greatest power of x is x to the first. Okay, so once you've identified x to the first, the highest power of x in the denominator, multiply by 1 in the form of the reciprocal of that power of x over itself. So that's the highest power of x. Its reciprocal over itself is the form of 1 I want you to multiply by. So it's an algebraic way of finding that limit. So if we distribute 1 over x to each term, two x times 1 over x becomes 2, minus 1 times 1 over x is 1 over x, divided by 1 over x times x is 1, plus 1 times 1 over x is 1 over x. And now we can utilize what we've learned before. The limit of the constant 2 is 2, minus the limit as x approaches infinity of a constant 1 over any positive power of x, and x to the first is 1 is positive, so this qualifies. That fraction will go to 0. And likewise in the denominator, that will go to 1 plus 0. And so we get 2. Okay. So that allows you to find this value. Now, before we went that far, I want you to, let's break this down a little bit. Technically, we should have used the property where you split the original problem into the limit of the numerator divided by the limit of the denominator. And if you tried, and I'm going to put air quotes around this, substitution, because you can't really substitute infinity because it's a concept, not a number, but just pretend like you've got a really big number. 2 times a really big number minus 1, that itself is headed toward infinity. And x plus 1 is headed toward infinity. And so what you get is infinity over infinity, which is indeterminate. This is an indeterminate form. There are other indeterminate forms that we will encounter. Another big one is 0 divided by 0 that you should know about. Those are some indeterminate forms. I'll put an S here to make that plural. 2 of the many that exist. And anytime you get that, that might actually, when you do the limit, become a real number like 2, like we just got. That infinity over infinity was 2. Infinity over infinity, just by looking at it, you can't necessarily tell what its limit will be, and you're going to have to do some kind of algebraic manipulation to find out what its limit will be. It could have been infinity, it could have been 0, it could have been -3, it could have been pi. There are lots of things it could have been. It just so happened that it was 2 for this particular problem. So, of course, getting a constant like 2 for a infinite limit implies that the graph has a horizontal asymptote at y equals 2. And something I like to do, so that I don't have to say on the right necessarily every time. A lot of times I leave myself a little bit more space, so I'm going to go back and change something. I'll leave myself a little bit more space with the infinity, just in case I can do what I'm about to do. So I intentionally will write the infinity with a little bit of extra bump there in the between it and the arrow. So I'll write infinity like out here. And after I get that, I might be thinking, well, as x approaches infinity, yes, it is definitely a horizontal asymptote on the right at y equals 2. But what about negative infinity? And I look through at my work, and I think about the process if I had used negative infinity instead. Well, when I get to the second step, 2 minus 1 over x going toward negative infinity will still be 0. And 1 over x will also go towards 0. So without having to write this work a whole second time with just one change being put in a negative infinity, I'm going to go back and put plus or minus infinity. Because at this stage right here, where I'm writing the plus or minus, it's at that stage that you realize it doesn't matter if it's positive or a negative number that's getting far away from 0. 1 over that positive power of x is headed towards 0. And so I can claim that this horizontal asymptote is actually true on both sides. Okay. Now, these would have been different up here. If this had been negative infinity, then in both cases we would have gone to negative infinity and negative infinity, which is still considered an indeterminate form of the same type as infinity over infinity. And in fact, you could have positive infinity over negative infinity. You could have negative infinity over infinity. Those all qualify as the same indeterminate form. So an extra negative sign or two in there does not change the fact that it's still indeterminate. And it's pretty much treated the same way. It's just if it's negative divided by negative, the answer will be positive. If it's positive divided by negative or negative divided by positive, the answer will be negative. And that's one thing you have to pay attention to. But otherwise, everything else would work pretty much the same way as it does here. All right, so if we look at the graph of this function, we just determined that it has a horizontal asymptote, y equals 2. We can look at the function and see that it's simplified as much as it can be, and anything that would make me divide by 0 at this point will give me a vertical asymptote. All right, so looking at this, x plus 1 will turn into 0 when x is negative 1, so that will give me a vertical asymptote at x equals negative 1. By the way, it's always good to think about all these types of things when you're trying to graph and make sure you're getting every one of them kind of, labeled and talked about. So we should probably write over here, there's a vertical asymptote at x equals negative 1. All right, so what does the graph look like? Well, it looks sort of like this. I'm not actually plotting specific points here. I'm just sort of graphing what it looks like. And you can see the curve approaches the asymptotes the further away you get from the origin. Okay, so that's just a little confirmation that what we found is actually correct. And by the way, as far as a sketching technique, finding your asymptotes is important, and when we're putting this all together later, that's one of the things that we'll look for are the asymptotes. So on the next slide, there are some guidelines for finding limits at positive or negative infinity if you have a rational function. And you may have heard of some of these before, and so it's a good thing. We have the algebraic technique that I showed you earlier, the highest power of x in the denominator. Its reciprocal over itself is a form of 1. We'll actually find all of these. Number 1, if the degree of the numerator is less than the degree of the denominator. I'm just going to make up some problems that illustrate these facts. So if the degree here is 1, and it's less than the degree of the denominator, let's make this x squared, then my suggested approach is, when you have something that looks like this, find the greatest power of x in the denominator, that's x squared, and multiply by 1 in the form of the reciprocal of that greatest power of x in the denominator over itself. And when you distribute to every term in the numerator and each term in the denominator, you should get 1 over x plus 2 over x squared over 1 minus 3 over x squared. And thank you. The limit of any constant over a power of x goes to 0. So the first fraction goes to 0, plus the second fraction goes to 0. The limit of the constant 1 goes to the constant 1, minus the next thing goes to 0, and that goes to 0. And that implies we have a horizontal asymptote at y equals 0. Okay, so if you look at number 1 again, if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function will be 0. So it's kind of a guideline so that you know what to expect. Number 2, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. Let's go up here to this one where it was 2x to the first over x to the first. The power of the numerator and denominator are the same, and they're saying that you can look at the leading coefficients, so 2 here and an invisible understood 1 here, and the ratio of those two constants will be your limit. This is a guideline. That's not the way I want you to find them. It's just a way to predict and know that you're right. I want you to do some algebraic manipulation. I want to see this times 1 over x times over 1 over x, or as in the case below, the form of 1 over x squared over 1 over x squared. I want to see that. But this guideline helps guide you to know what that would look like. And in fact, I imagine some of you in a pre-calculus or college algebra class may have heard that trick before, and that's a nice one. So it helps you understand where the answer is supposed to be headed toward. Okay, then if the degree of the numerator is greater than the degree of the denominator, let me make up an example like that one. Let's do x squared plus 5 over, and the degree of the numerator is greater than the degree of the denominator, so let's make this x minus 1. The greatest power of x in the denominator is x to the first, so my trick says to multiply by the reciprocal of that greatest power of x in the denominator, so 1 over x, over itself as a form of 1. And distributing those 1 over x's, we will get x plus 5 over x divided by 1 minus 1 over x. And I'm kind of doing this in air quotes. As x goes to infinity, the very first term is going to go toward infinity, not a number, but kind of the idea of, plus the next thing will go to 0 because it's a constant over a power of x. The limit of 1 will be 1 minus 0. So this is going to go toward infinity. So that line I just wrote here is sort of a thought process. It's not really legal to put infinity in as if it were a number like that, but it's a good thought process. Huge number plus 0 is still huge. Divided by something that's getting closer and closer to 1 is that huge number. So this is going to positive infinity. And this does not have a horizontal asymptote associated with it. And what that means is, if we looked at a graph of something like this, it means that the graph is going to, and I'm going to make up because I have no idea exactly what this looks like. Well, I'll graph it on my calculator because I want to at least present a pretty decent idea of what it looks like. So excuse me for a second while I plot this quickly on my calculator. Let's see, I said x squared plus 5 divided by x minus 1. Well, one thing I can do is we'll have a vertical asymptote at 1. That much I can tell you for sure. And in fact, it has a slant asymptote. If the degree in the numerator is exactly 1 more than the degree of the denominator, there's what we call a slant or oblique asymptote. And to find the equation of that slant asymptote, you do polynomial long division. And don't forget that when you do polynomial long division, for any missing term, you're going to need to put in a 0 so that things line up nicely. Just a little short reminder of that. Then what do you multiply x by to get x squared? The answer is x. X times x minus 1 is x squared minus x. Then you got to subtract. Be careful that you subtract both terms, not just the first one. X squared minus x squared, of course, is 0x squared. That's what we designed it to do. I don't ever write that 0x squared down. And then 0x minus negative x is positive 1x. Then bring down the 5 and repeat. What do you multiply x by to get x? The answer is positive 1. So put plus 1 up there. 1 times x minus 1 is x minus 1. Then you subtract. X minus x, of course, is 0. 5 minus negative 1 is 6. And so y equals x squared plus 5 divided by x minus 1 is equal to the quotient part of that, x plus 1, plus the remainder part of that, 6, over the divisor, x minus 1. And you know that 6 over x minus 1, that part, as x goes to infinity, gets closer and closer to 0. And so what's left is it's getting closer and closer to the quotient part of this, x plus 1. And so the slant asymptote equation is always going to be y equals the quotient part of the answer, and the remainder over divisor part will go to 0. So there's the equation of the slant asymptote. Let me plot that. Okay, and I never hit graph. Hold on, gotta do that. The graph looks something like this. Don't see much of it, so I'm going to need to zoom out a bit to see a bigger portion of it. But it looks something like this. And like this. I could have made those asymptotes a bit longer on the right side. Oh well. So, if you notice on the right side, as x is going towards positive infinity, the y values are just going to continue to rise towards positive infinity. And so that just means that the graph on the right side, as x gets bigger and bigger, y is unbounded. It just gets bigger and bigger as well. Okay, and that's going to happen when the degree of the numerator is greater than the degree of the denominator. All right, so if you consider the power of x that's the greatest power of x, you might realize that the reason that what I'm saying works is because an x squared, for example, in this example you can still see kind of at the top of that page, the x squared there gets very much bigger than x does. Although they're both going toward infinity, x squared is more influential. And so, whereas x is getting big, and plus 2 won't change it by much, x squared is getting huge by comparison, minus a little insignificant 3. And so you have big divided by tremendous, which it stands to reason that that's going to head towards 0 because the x squared is way more influential. Whereas in the second example down there near the bottom on this page, x squared in that one is huge divided by big, and the numerator being much bigger than the denominator makes sense that that would go to positive infinity. And the first example we did, where the powers of x were the same, the 2x minus 1 and the x plus 1, they're both getting big at about the same amount of influence, and so the only difference is the coefficient of x in each case becomes the most influential factor, because otherwise the x's sort of are about the same idea. And so the only difference is you're doubling big on the top versus just having big on the bottom. So it's twice as big, and it ends up being 2 in that case. Okay. So if we looked at this graph, or this limit, let's say first, and then we'll talk about its graph. The limit as x approaches infinity for the function 1 over x squared plus 1 totally makes sense that this will head toward 0 because you're dividing a constant by basically a huge power of x. Well, 2 is not that huge, but anyway, a power of x, and that will head towards 0. And it works for negative infinity as well. And if you look at the graph of this one, it looks sort of like this. And in fact, this is a special case of a type of function that an Italian mathematician whose last name was Agnesi, what he looked at was something of that form, f of x equals something in the form of 8a cubed, where a is a constant, over x squared plus 4a squared. So you can see how that's sort of related to the one we just did. And all the graphs of this type have that kind of curve. And in fact, sometimes it's kind of pronounced like this. And when you get the right curvature, it sort of looks like a witch's hat, right? Of course, it's really supposed to go on forever. But and so this type of curve is called the witch of Agnesi, because that kind of looks like a witch's hat. So just a special name for this curve. And of course, what interests us is that the asymptotes, horizontal asymptotes that we get at y equals 0, because that limit gives us an answer of the constant 0. All right. Now, as it turns out, all rational functions, polynomial divided by polynomial type functions, have the same asymptotes on the left and right hand side. If there's a asymptote of y equals 4 on the right, there'll be an asymptote of y equals 4 on the left. And that's why I earlier said you can leave a little space and do that plus or minus thing, because very often they end up being the same limit. You can save yourself writing it twice that way. But if you have any kind of alteration to that, like put in a radical or something, the limits from either side can actually go to different numbers. Let's do that here. Let's make it look like it's sort of a rational function. So far, so good. And this is 2x squared plus 1. So still looks like a rational function until I put a square root radical in there, and that messes it up. So this particular function might have different limits on the right compared to the limit on the left. So let's find this limit, and then we'll do the process as if x were going towards negative infinity next. I still want to use my trick that I told you earlier. What is the greatest power of x in the denominator? Well, I see the square root of x squared. So that's going to be my thing whose reciprocal I take. The square root of 1 over x squared is the highest power of x in the denominator's reciprocal. Now, in the denominator, radical times 1 over radical totally makes sense, because we're going to do radical arithmetic here in a second with that. But in the numerator, there is no radical in the original numerator of that fraction. So I really don't want to use the radical expression. So what is the square root of x squared equal to? Well, if x is, say, 4 4 squared is 16, the square root of 16 is 4, you get back what you started with, right? But what if it's negative 4? Negative 4 squared is 16, the square root of 16 is 4. I'm not getting back the original negative 4, I'm getting back the opposite of that negative 4. And that happens every time x is negative. You'll get back the opposite of what you started with. And when x is positive or equal to 0, you'll get back what you started with. By the way, that's the definition of the absolute value of x, which means that algebraically, the square root of x squared is the absolute value of x, by the way. It actually goes both ways. Okay, so since x is headed towards positive infinity over here, x will be positive, which means that 1 over square root of x squared in that case will be 1 over x. Square root of x squared is replaceable with x because x is positive in this problem. Okay, so distributing, we get 1 over x times 3 over x is 3 minus 2 over x, okay, in the denominator. When I multiply that, I'm going to get the square root of 2 plus 1 over x squared. All that's under the radical. Let me give you a kind of an aside so you understand what I just did. If I were to multiply those two radicals, we would have the original radical would be like over 1 times 1 over the other radical, which would give us this quotient of the two radicals. Then that quotient can be written as one really big radical of the ratio of the arguments. Then I can split this into 2 over x squared over x squared plus 1 over x squared, which gives me what I have over there. When you simplify 2x squared over x squared, you get 2 plus 1 over x squared. Okay, so as x goes to infinity, the constant 3 is 3, minus constant divided by power of x goes to 0 as x goes to infinity. Then under the radical, the limit of the constant 2 is 2, plus the limit of constant over power of x goes to 0. And so this goes toward 3 over the square root of 2, which is 3 squared root of 2 over 2. And that implies that our function, if we were to graph it, would have a horizontal asymptote at y equals 3 squared root of 2 over 2 on the right side. So when you do x approaching infinity, unless you've given a lot of thought to it, you can't assume that that's true about the left side as well. We're actually going to need to do x approaching negative infinity to see what's happening on the left side. Okay, so we're going to do the exact same function's limit, but this time we're going to have x approach negative infinity. All of the algebra that we did doesn't depend on the kind of number x is to perform it. So I'm going to do exactly the same algebra steps as before. Well, except for this one. This is where it's different, right here. What is the square root of x squared if x is negative? Because as x goes to negative infinity, x is a negative number. If you look up to the right, and unfortunately I kind of covered it up, let me go back up there. What is the square root of x squared when x is negative? It's negative x. So I can't replace square root of x squared with x here. I have to replace it with negative x. And that's the big difference here. That's what's going to change as we do this. Because x is negative, it changes what that radical would give us. Okay, so multiplying that will be negative 3 plus 2 over x over the square root of 2 plus 1 over x squared. That's the algebra I really meant to say is the same. And the limit of the constant, negative 3 is negative 3, plus the limit of constant over power of x is 0 as x goes to negative infinity. And this will be the square root of limit of the constant is constant, plus 1 over power of x goes to 0. And this is negative 3 over the square root of 2. Which is, of course, going to rationalize to be negative 3 squared roots of 2 over 2. Which means that we have a, whoops. Well, it's not doing what it's supposed to do. Well, if you can't do it one way, you do it a different way. I can fix this. Okay, that implies that this has a horizontal asymptote at y equals negative 3 squared roots of 2 over 2 on the left side. And these happen to be opposites. That doesn't have to be the case either. It just so happens that this time they are. And if you look at the graph of this function, the graph of f of x equals 3x minus 2 divided by the square root of 2x squared plus 1. It looks like this. So I got all set up with the asymptotes, and it looks like something like this. Well, there. Okay. That's sort of what that looks like. And that's not a sharp point down there at the bottom. I just made it look that way. It's a nice smooth curve there. Not a funny point. And of course, you get this on your calculator and see a better rendition of it. That would probably be a good idea. Okay, so notice that this is not a rational function, and that means that the asymptotes on the left and right side, if they have any, don't have to be the same. All right, so a lot of functions do not approach a finite limit as x increases or decreases without bound. In other words, we've been getting numbers like 3 squared roots of 2 over 2 or negative 3 squared roots of 2 over 2 or whatever, but not all of them do that. For instance, if you have a polynomial function, like the limit of x approaching infinity of 3x squared plus 2x plus 5 is simply infinitely large, it certainly doesn't have a limit that is a constant. All that would tell us is that on the right side, the right-hand side goes up without bound. As x approaches infinity, y approaches infinity. That's all that that would really tell us. So this next definition, definition of infinite limits at infinity, helps us to describe the behavior of polynomial and other functions at infinity. So let f be a function defined on the interval from a to infinity. The statement, the limit of f of x as x approaches infinity equals infinity, means that the values will just increase without bound. I'm not going to go into all that jargon. What they're saying is true. I just don't think you need to worry too much about it. And the statement, limit of f of x as x approaches infinity equals negative infinity, means that the further to the right you go towards positive infinity, the further down you'll go towards negative infinity. And so if you get an answer of infinity, your graph's going to sort of look like that. If you get an answer as x approaches infinity of a negative infinite number, your graph will look sort of like that. Okay? And then you can do the same kind of thing as x approaches negative infinity. You could have as x approaches negative infinity, y could approach negative infinity, meaning your graph will look like that. Or as x approaches negative infinity, y, oops, I didn't write that in the right place. Let me back up, give myself more room. As x approaches negative infinity, the outputs could be getting infinitely larger towards positive infinity, and the graph would look like that. So these are the possible end behaviors if you get an infinite answer for a limit as x approaches positive or negative infinity. And that's, graphically speaking, what's going to be happening. Okay? So let's see what else we have here. So let's find a couple more limits. I don't have a whole lot left to go, so I'm just going to move over here a little bit to the right. Whoops, not that far. And move up a bit. Okay, I can still see a little bit of that over there, but that's okay. All right, so for this example, let's look at the limit as x approaches infinity of a pretty simple polynomial function, the cubing function. So as x gets bigger and bigger, you'll be multiplying positive times positive times positive, big, big, big. That's just going to get even bigger and bigger. And positive times positive times positive will make that go to positive infinity. And what that means is the right-hand behavior of this function is going upward on the right side. Okay. Now, let's do another one. Same function. Let's look at the left-hand behavior as x approaches negative infinity for x cubed. Infinitely big times infinitely big times infinitely big is just really big. But this is negative times negative times negative, which is going to be negative really far from 0. Negative times negative times negative is a negative answer. And what that tells us is the left-hand behavior, as x goes to negative infinity, this is going to be going down. Okay? So this is not talking about what's happening in close to the origin. This is just, if you looked at the graph of this, you can tell for sure that this side will go down according to this statement, and this side will go up according to that statement. And what happens in the middle is, going to be governed by the rest of the function. As it turns out, this is a really simple one. So when you get close to 0, it just goes closer and closer to 0. And then like this. And I didn't do a good job of guessing the curvature. So let me just erase a little bit of that pink So it looks like I meant for it to look like this. Okay, so that's what that graph actually looks like. So we're predicting end behavior. Okay, so I'm going to repeat something I hope you heard before this, but if you're graphing a polynomial function, if f of x is x to the nth plus a bunch of other stuff, and it could be minus, there are two big possibilities. If n is even, like x squared or x to the fourth or x to the sixth, there's one type of behavior you'll expect. And that is, if n is even, you'd expect the n's to point in the same direction. So they'll either both point up with unknown stuff going on here in the middle. I'm just going to squiggle that because that's not predicted by this at all. But the end behavior is both sides up or both sides down. Left and right, both down, with unknown stuff here in the middle. So it opens upward when, oops, I forgot to write in something there that's really important. Oops, let me fix that. A sub n is just the coefficient for the x to the nth term. It'll open upward if a sub n is positive. It'll open downward if a sub n is negative. Okay, all that makes sense? Okay, you maybe have heard that before, and I kind of hope you have. I hope this isn't the first time through. Now, what if n is odd? Well, that means that the two ends will open up in opposite direction. So either the right side is up, which means if the other one's going the other way, the left side would go down, or the right side will go down with unknown stuff in the middle, and the left side will go up. And again, you can predict that based on the leading coefficient. That's what a sub n is called, is the leading coefficient. If a sub n is positive, the right side goes up, which means the left side has to go down. If a sub n is negative, the right side has to go down, which means, of course, the left side goes up. So if you notice, the thing that you have in common is when a sub n is negative, the right side goes down. When a sub n is positive, the right side goes up. Then all you have to do is remember when n is even, they go the same direction. When n is odd, they go in opposite directions. So anyway, I thought maybe you heard that before, and what we're doing now kind of reconfirms all of that, puts it in a similar focus so that we can kind of know what to expect. All right, so that ends this lesson. I'll see you in class.